If you fell into a black hole, the honest answer to what happens next is that physics gives two different accounts, and both of them appear to be correct. Not two guesses, two rigorous descriptions, one from your point of view and one from everyone watching, that cannot be reconciled into a single story about where you are. This is still unexplained. The science that hasn't finished arguing. So what does the fall actually feel like from inside? Why does someone watching from a safe distance see something completely different, and is one of them wrong? And what happens to everything you were made of, given that the universe is not supposed to be able to lose information? That last question has occupied theoretical physics for 50 years and is not closed. Begin with what a black hole is, because the popular image is misleading. It is not an object sitting in space, and it is not a hole in anything. It is a region where mass has been compressed so tightly that the curvature of space-time becomes extreme, and every possible path forward in time leads inward. That is the whole definition, and it matters for everything that follows. The boundary is called the event horizon, and it is not a surface. Nothing is there. No wall, no membrane, no change in local conditions. It is simply the last place from which light can still escape outward. Cross it, and every direction that used to mean forward now points toward the center, which is why escape stops being difficult and starts being geometrically meaningless. Here is the first genuinely strange consequence. For a sufficiently large black hole, crossing that boundary is uneventful. There is no jolt, no barrier, no alarm. Einstein's equivalence principle says that free fall feels like floating, and it does not stop being true at the horizon. You could cross the point of no return without noticing that you had. Size decides how gentle it stays. Tidal force is the difference in gravity between your head and your feet, and it depends on how sharply the field changes across that distance. Near a small black hole, the change is brutal. Near a supermassive one, millions of times the sun's mass, the horizon is so far from the center that the gradient across a human body is mild. The horizon of a black hole with 4 million solar masses, like the one at the center of our galaxy, sits about 12 million kilometers from the center. And at that distance, the pull on your head and your feet differs by an amount you would not detect. For a stellar mass black hole, the tidal difference would tear you apart long before you reach the horizon. Physicists call it spaghettification, and the word is doing real work. You would be stretched lengthwise and compressed sideways into a thin stream. For a supermassive one, you would sail across the horizon intact and have some time afterwards. Now the view from outside, which is where the two accounts split. Gravity slows time, and near a horizon it slows it enormously. As you fall, an observer watching from a distance sees your clock running slower and slower, sees your movements crawl, and sees the light leaving you stretched to longer and longer wavelengths until it fades out entirely. From their perspective, you never cross. You approach the horizon, dim, redden, and freeze, and the image of you fades into nothing without ever quite arriving. They will wait forever and never see the crossing happen, because the light that would carry that news can never reach them. Meanwhile, you crossed in a perfectly ordinary few seconds by your own watch. There is a practical consequence to this. Every black hole anyone has ever observed is, from our frame of reference, still forming. Its collapsing matter frozen just outside the boundary and fading. Neither account is wrong. This is the part people resist, because it sounds like a trick. It is not. In relativity, there is no universal now, and simultaneity is not a fact about the universe. It is a relationship between an observer and an event. The two stories disagree about when things happen because when is not a shared quantity. Inside, the geometry does something to your idea of direction that is genuinely hard to picture. The radial direction, inward, takes on the character that time had outside. Falling toward the center stops being a direction you could turn away from and becomes something more like next Tuesday. You cannot steer away from it for the same reason you cannot steer away from tomorrow. This is also why firing your engines does not help, and why it actively hurts. Accelerating changes your path through space-time in a way that shortens the proper time you experience before reaching the center. The counterintuitive advice, if you ever need it, is to fall freely. Struggling gets you there sooner. What waits at the center is where the theory admits defeat. General relativity predicts a singularity, a point where curvature becomes infinite and the equations produce values that are not numbers. Physicists do not treat that as a discovery about reality. They treat it as the theory announcing that it has been used outside its range. The reason it fails is specific and well understood. General relativity describes gravity and works superbly at large scales. Quantum mechanics describes matter and works superbly at small ones. A singularity is enormous mass in a vanishingly small space, which is precisely the one situation requiring both theories at once, and we do not have a theory that combines them. Now the deepest problem, and the one that made this a 50-year argument rather than a curiosity. In 1974, Stephen Hawking showed that black holes are not entirely black. Quantum effects at the horizon cause them to radiate very faintly, lose mass over unimaginable timescales, and eventually evaporate completely. The trouble is what that radiation carries. As calculated, it is thermal, essentially random, and depends only on the black hole's mass, spin, and charge. It does not appear to encode anything about what fell in. So when the black hole finishes evaporating, the information describing everything it swallowed seems to be simply gone. Quantum mechanics does not permit that. Its evolution is reversible in principle. Given a complete description of a system now, you could in principle reconstruct its past. Destroying information outright is not a strange result within quantum theory. It is a contradiction of one of its foundations. That is the black hole information paradox. It is worth being clear that this is not a puzzle about our instruments or our cleverness. It is two of the most successful theories in the history of science making incompatible claims about the same event. For decades, the disagreement was open enough that people bet on it. Hawking himself argued information was lost, then conceded in 2004 that it probably is not. The current consensus leans toward preservation, with the information somehow encoded in the radiation in a way that is not visible in the original calculation. How exactly is the unresolved part? Several serious proposals exist. One says the horizon behaves like a hologram, storing a complete description of everything inside on its two-dimensional surface. Another suggests the interior is not smooth at all, but ends in a wall of high-energy particles, which would mean the fall is not gentle, and an infalling observer burns at the boundary. That second idea is genuinely uncomfortable, because it contradicts the thing we started with. If there is a firewall, then crossing the horizon is not uneventful, and Einstein's principle that free fall feels like floating fails at exactly the place we most wanted it to hold. Either something we are confident about is wrong, or something else is, and nobody can yet say which. Recent work using calculations of quantum entanglement has produced results suggesting information does escape, and has reproduced the curve that preservation requires. It is progress, and it is not a complete answer, because the calculations do not yet explain the mechanism by which any particular fact about you gets out. The calculations rely on techniques developed for entirely different problems, which is often how these things break open, and they have shifted the question from whether information escapes to how. So the summary is unusually honest for a physics topic. You would fall in without feeling the boundary, if the hole were large enough. Everyone watching would see you freeze and fade and never arrive. You would reach a region the theory cannot describe, and whether anything of what you were survives in the radiation is the open question at the center of modern theoretical physics. Which is why physicists keep returning to it. A black hole is the only place in the universe where our two best theories are forced into the same room and made to disagree in public. Whatever resolves that argument will not just tell us what happens when you fall in. It will be the thing that finally tells us what space and time actually are. The universe keeps refusing clean answers. Subscribe and meet the next one, the place on Earth where GPS quietly lies.